So, well, today's quite short, so I'll try to pack in a couple things that I still wanted to say about jet substructure, and a few words about jets at the LHC, sort of why they're problematic or what's difficult about them. That basically also applies to, say, Rick physics and so on. And it's something that we actually don't have to worry so much about at the IC. So that'll be the first part, and then I'll talk a little bit about jet substructure, just very roughly how we do calculations, probably skip a little bit. And then I'll talk a little bit about machine learning that can help us to actually identify where the jets are coming from, right? If it's like a quark jet or a gluon jet, or if it's like a Higgs and so on, right? We discussed this a little bit at the beginning, so that'll be the last part. Okay, so maybe I showed this illustration before, right? But at the LHC, where we have these kind of complicated events, right? There's like a lot of jets that are being produced. And ideally, right, as I illustrated, I think at the beginning, right, like one of these jets should just be a quark or a gluon, or any other particle at very small distance scales. And so we sort of the naive picture that we also kind of followed in the calculations, right, that we did yesterday. Right? So we have a hard scattering here at the center, and there's a hard parton at high energies that is produced here, and then it sort of fragments and produces additional radiation, right? And we measure, for example, the transverse dimension of the jet, right? That's kind of what we discussed here, right? In these calculations, right? Where we start with, say, a particular quark, then we get this function here that tells us how much energy is actually contained in the jet, and that allows us to compute some of these cross sections here. Now, sort of to illustrate that again a little bit, what you can see here is exactly that kind of picture that we followed in the calculation, where we have two incoming protons. There's a hard scattering of quarks and gluons, either one, and then that will produce the jet that we observe, right? We do an inclusive measurement, so right, we'll measure this jet, we'll measure this jet, we'll measure all of them, right, one at a time, and that's sort of the picture we follow in the calculation, right? The problem is, though, that there's a lot of additional contributions that are often really hard to get under control. And so one of them is that you see here. So basically, before this collision actually happens, there's also emissions that happen from these incoming quarks and gluons that eventually scatter, right? So they can produce what is called initial state radiation. And like that sort of fills the event and the entire event, right? And some of it, right, will land in that jet. And that's something that we wouldn't account for, right? If we only think about it, as a quark or a gluon that starts here and produces the jet, right? That's something we don't actually take into account necessarily, right? That's what is very difficult to take into account. There's a lot of other things happening as well, right? For example, in one proton-proton collision, where we not only have like this one hard scattering, right, that produces the jet we're interested in, but it can be other secondary scatterings as well. That's often referred to as the underlying event or multi-parton interactions. And similar to the initial state radiation, it sort of produces soft emissions that are really distributed everywhere at the event. And again, some of those are going to end up in the jet that we're interested in. Also, we did a calculation. We briefly talked about this yesterday, where we're doing it, the calculation at the level of quarks and gluons. But of course, when we actually measure our hadrons, right? So that's why we go from, say, these arrows to circles, right, to illustrate that. In general, you also have to worry at high luminosities, basically about multiple PP collisions happening sort of in one bunch crossing. Where you basically have like bunches of particles that go around these circles in the collider, and then you have crossings of bunches, right? And it's not just necessarily one collision that happens, but many collisions can happen, right? It's very difficult to disentangle those. Yes.
These initial state radiations affect the hadron distribution, which we mentioned.
Right, I'll get back to that later. How much what happens with these contributions? Okay. Right, so that's an additional thing, right? That again, produces soft particles. I mean, I just draw, the lines that end up in the jet here, right? But of course, they sort of happen everywhere, not just in the jet. And then there's something called a non-global structure. And that is referring to other jets that are produced in the event, right? Here, there's like one jet here, put a third jet here, right? Like we saw, there can be like 10 jets, right? And it turns out that there are so-called color correlations that again lead basically to soft emissions basically from this sort of color dipole that you see here. And so these jets are not produced in isolation, but there's actually color connection between the two jets, right? And again, that can lead to soft radiation, right? And so we have to worry about these, you know, even though it's an inclusive measurement, we try to sort of measure one jet at a time, but actually this can also matter, right, in the end, right? And so it again, you know, leads to potential problems. And so at the LHC or in general, at say RIC, right, where we have QCD initial state, we have to worry about all these different things, right? And like some of those we just don't have under control from first principles. It's like something like pileup, we sort of try to correct for the underlying event. We don't really understand from first principles. Initial state radiation, we don't really control well because it's a subleading power effect. And well, the non-global structures we can to some extent deal with. But it generally makes it much more complicated, you know, than this initial picture, right, where they have a quark or a gluon that just produces a jet. So the question, you know, as you just asked is like, you know, how, you know, is this a problem, right? And do we have to worry about all these different contributions, or can we just ignore them? Maybe they're sufficiently small, right? We don't really need to worry. And the answer to that question is, well, it kind of depends, right? It depends on what question we ask. And so what I showed you before, right, where we had this really, what I showed yesterday, where we had this very good comparison between theory and data. If I just look at the cross section here, differential in the jet transverse momentum here, right, of several orders of magnitude for different rapidity bins, right, then it doesn't really matter. So if we're only interested in the total energy of the jet, right, say that's like 500 GeV, then I don't really care if there's a few, you know, order 1 GeV particles in it, right? It doesn't really matter too much. And that's indeed what you find. But if you do a theory data comparison, then for that particular question, right, for that particular observable, we don't really need to worry about it, right? It's like small effects that we can, you know, easily correct for. But if we ask questions and that, you know, then goes in the direction, right? So here, right, we're completely agnostic to where the jet is coming from, right? Whether that's a quark or a gluon or a W or Higgs, right? They all have like, that's like a jet with a particular momentum, right? What we would like to do with these jets is, for example, to measure their mass, right? Like you want to weight them, right? Like is it, you know, a very heavy jet, right? Particularly, you know, heavy mass, then that could originate, say, from a Higgs boson as opposed to a quark or a gluon. And so what we want to do, for example, is measure its mass, right? And then it turns out that all these different contributions that I just showed are super important. That's what you can see here. If you want to measure the mass of a jet, so the mass of a jet is really just defined as the sum over the 4 vectors of all the particles that are in the jet, and then you just square it. Okay, so that's really just the jet mass, and it tells us, you know, how heavy that is. And that's really a separate scale, right, from the total energy, right? We measure the transverse momentum relative to the beam, and then in addition, you know, we sum over all the particles here and add up their four vectors, right? So that's the mass, right? And so for QCD jets, that's what I briefly showed yesterday in the questions. We get this distribution shown here, right? Like the mass of the jet, like typical mass. So this is like, you know, for jets, you know, between 300 and 400 GeV of energy. Then the mass of the jet distribution looks like this. It's, you know, alpha theta here. And so typical mass is around, you know, 60 GeV or something. But if we do a perturbative calculation, like a purely perturbative calculation, without worrying about all these other effects here that we don't necessarily understand very well, then we get this yellow distribution here, right? And so that difference, right, the difference between the yellow and the red curve, right, or the data is all these different things here, right, that also happen in these collisions, right? So in that sense, right, it's sort of in proton-proton collisions, it's generally a little bit difficult to think about it really sort of in this idealized picture that one jet directly corresponds to a quark or a gluon, or at least it depends on the question we're asking, right? If this apparently is a very bad question to ask, right? Then we sort of lose this sort of naive interpretation, right? We have to worry about it. So the question is what to do about this, and of course, but if we and that's what I'll talk about in the context of machine learning, right? If we want to know, is this jet now actually coming from a quark or a gluon, or is it, you know, any other particle that initiated that jet? Then of course, what I need to do is I need to look at the substructure of particles, right? I need to measure something else besides its total energy, right? And then I basically need to figure out what I do with all these different contributions, right? Okay, so it turns out there are techniques that are developed sort of over the last 5 years or so that allow us to deal with this in a systematic way. And so that goes by the name of jet grooming. More or less what it does, it systematically removes soft radiation from these jets. So the good thing that we can make use of is that we know this is generally soft radiation. It's not the hardest radiation in the jet. And then what we can do is just try to systematically remove soft particles from the jet. And there's of course different ways how one could do that, right? I could just say, well, any particle that's say less than 2 GeV, I'll just remove that. The problem is if I did that, then I cannot compute anything anymore, right? That would be completely IRC safe, unsafe, right? And that would sort of spoil the whole idea about jets, right? That I used them in the first place, right? That I able to do computations and compare one-to-one theory and data. So if I just in a naive way remove particles from the jet that are just soft, right? That's not really the way to do it, right? But there are other ways to do it, and so I'll briefly mention those on the next slides. Are there any questions about the thing so far? No, everything clear? Okay. All right. So generally speaking, if we want to think about jet substructure, jet mass is one of the examples of jet substructure, then we want to look at the radiation pattern inside these jets. And so what you can see here as an example is a quark jet. It's a typical quark jet. It's like one example of a quark jet that is like simulated with lithium. All right. So what you see here, it has this circular shape, and most of the energy is sort of at the core of the jet. Okay. That's very typical for a quark jet, right? There's not sort of it's not more spread out. That would be the case for a gluon jet, or for say a Higgs, that would be two prongs, sort of two hotspots in the jet. Right here is everything sort of at the core, right? So this is one particular jet, and if you average over many of those, then that's exactly what you find, right? Like you see here, a lot of energy is at the core of the jet, and then I don't know whether you can see this a little better on my laptop, but you sort of see that it just falls off, right? So it's very likely a lot of energy is really directly at the core of the jet, right? And so that's basically the pattern that we want to make use of, right? Like if I look at that jet, this looks like a quark jet, right? But of course, we want to make it quantitative, right? We want to compare that to other jets, right, that originated and that look differently, that originate from different particles, right? Then we have to make use of the radiation pattern and then how the energy is distributed in the jet. And then potentially we can say, at least on an event average basis, we can say, are these jets in general more quark-like or are they more gluon-like? Okay. So I want to skip a little bit here, but just to say a few words about the calculation in general, how we do jet substructure calculations in general. So this is very similar to what we discussed yesterday. This is the cross-section differential in the jet kinematics. So in the total jet transverse momentum and its rapidity, so the polar angle relative to the beam axis. And then we basically get the same factorization as I showed yesterday, right? We have the two PDFs that we get from global analysis. There's a hard scattering piece, right? And then I have here a jet function, right? That's the jet function we computed yesterday, except that yesterday it was only dependent on Z, right? This momentum fraction tells us how much energy is contained in the jet relative to the initial parton. And now this jet function also depends on an additional variable that I just call tau here, right? That's basically any jet substructure variable that we may want to think of. For example, the jet mass. Okay, so what I want to show with this is that all we really have to change if you want to think about jet substructure, right? If you want to be differential here in an additional variable that only affects the internal dynamics of the jet, then all we have to do is we have to switch out that jet function that we saw before, and now we'll make it more differential. Okay, so I only really have to, in the perturbative calculation, I don't have to change everything, right? I can keep most of the cross section here the same, and all I'm going to do is basically switch out that last part, right? The jet function that tells us how this changes. And so basically we'll have to go ahead and compute this. I just want to give one example that's very relevant for nuclear physics, even though I don't want to go into details here, but one of sort of the standard observables is that's interesting to study non-perturbed dynamics and for nuclear physics is that you measure the hadron distribution inside the jet. So what I mean by that specifically, this momentum fraction ZH, where I basically just look at all the hadrons in the jet, and I divide it by the total jet PT. So this is basically the longitudinal, the Cornell momentum fraction. So it tells us how much of the total jet transverse momentum is carried by the hadrons in the jet. So it's basically now a more differential measurement, right? These three variables here, I just switch out here the jet function. That's not written as curly g, but it's the same thing where I have now the dependence on two variables, the z and also this additional jet substructure measurement. And then what I basically do is I go ahead and do again, say an next leading order computation of this object that now depends on these two variables. And so you see some of the things that we also saw yesterday, by the leading order, for example, we have the scalar function, 1 minus z, now at leading order, there's another piece here. We have again these plus distributions that we saw yesterday that are part of this jet function that we discussed about yesterday. Now the additional terms here, now in this new variable. Okay, and so that's generally how we can do say fixed order computations for these kind of jet substructure observables. And well, in this case, because that's really just fixed order computation essentially, or up to using this factorization, then we can directly compare to data. That's not as difficult as the jet mass. So what you can see here is comparison to ATLAS and CMS data, plotted as momentum fraction ZH of the hadrons, right? So it's a quantity between 0 and 1. And you can see that overall actually works very well. Like that looks sort of like a typical fragmentation spectrum that you often measure, for example, in the plus or minus collisions, or that you measure semi-inclusive deep elastic scattering, right, where the cross-section basically just dies off here as you go to larger values in CH. Right? Now that's basically measured as a substructure variable, or as a substructure measurement, right? But it's sensitive to the same collinear fragmentation functions, that we would normally use to describe hadron production measured in the entire event. Here it's like just in the jet. Okay, so this is one example where we can actually do this very well. Let me check. Yes. So now coming back to the jet mass distribution, and let me see if I have okay, I forgot the reference where I got this from. There's a paper, if you're interested, I can tell you where that is. So what we're changing now here, if we're interested in the jet mass, is we still have the jet kinematics in this cross section, and now tau is given by the jet mass squared, right, divided by pt squared, just to make it dimensionless. And this is really just the sum over 4 vectors squared, right? So this is really the jet mass. So this is problematic observable that we would like to use, but it turns out to be kind of difficult, right? Because it has all these additional contributions. And so that calculation that you saw here can now be done in the following way. We use again this function here, but we have to resum additional logs in this jet mass variable, right? So if we just do this measurement, we can basically just compute this quantity here at fixed order. But if you want to look at the jet mass, then this ratio here is typically very small, right? You saw the jet mass is typically much smaller than the actual jet transverse momentum. And so we have to do additional work to actually make sure these logs don't sort of spoil our perturbative expansion, right? This is a little bit fast here, but I just want to sort of give a little bit of an impression of how this generally works. So we basically write down again this jet function, but as opposed to evaluating it just at fixed order, we now have to refactorize it, right? That's sort of the same idea as we had here, right? If I have a factorization, that means there are different energy scales associated with that factorization, and I can resum those by writing down the factorization and solving the associated renormalization group equations, right? And I can do that here in this case. I have a hard function, I have a collinear function, and I have a soft function in this case. So I think you've heard a little bit about soft functions before, but in I think Matt Siever's lecture, that's a little bit of a different soft function, but sort of the same idea, right? If I want to do the resummation, make sure everything's under control, then I have to do an additional separation of scales. Okay, and so if I do that, calculation, then what I'm getting is basically what I showed before. Then I'm getting this yellow result, right? And so that's kind of a problem. So the question is how we fix it now. Okay. So the way to fix it, or one way to fix it, is, as I said, we can remove soft particles. Okay. And so as opposed to just taking the jet, as you can see here, and just looking at where the soft particles are and just removing them one by one, what we can do is to make use of the clustering history. So that's right. So this is what I mentioned before. So here you identify the jet first with the anti-KT algorithm to make sure it's round. And then you take all the particles and you recluster it. You basically just run the algorithm again, but now you run it with a Cambridge-Hoffman algorithm. Right? And what that does is it gives you a tree structure that looks like this. Okay, so here basically have the main branch of the jet, and any subsequent emissions that come off of that branch are at smaller angles. Right, this is the largest angle. This next angle is smaller. This angle is smaller, and so on. Right, so by using that algorithm, we basically generate that tree. And the last particle you put in the jet is the one with the largest angle. Right, because we have a list of distances or angles, we cluster them, we start with the smallest one and the one with the largest angle. So this one basically will be put in last into the jet, right? And so by running that algorithm, we can generate these kind of tree-like structures, right? And also if you look at these branches that come off the main tree, also here, they're basically ordered in angle, right? Like for example, here, this angle is larger than the next one. And this angle here is larger than the total angle relative to the main branch. Okay, does that kind of make sense that we get that structure from the jet algorithm? Yes.
Why do you need to keep the far left, the far left, like branch?
This one?
Yeah, maybe I'm misunderstanding this one, but why would you add that in if it's not going to help it?
So it's added in because that's what the algorithm tells me.
Oh, okay.
So I first run this algorithm, right, for the anti-KT, and I get a group of particles, right, and then I run the Cambridge-Hoffman algorithm, and that basically produces, you basically run it until all the particles that you found at first are included again in the jet, right, and that gives me the tree structure. Okay. Right. But yeah, I mean, you're correct, right? Like, so maybe we should remove this one, right, because it's soft, right? Exactly. Well, and that's exactly what we do, right? So this is basically the last one, right, that I put in the jet, right? So I start with the smallest angles, and then what we want to do is basically start from the end, right, and sort of go backward through the clustering history and look at those that are particularly soft, right? And indeed, also what we're going to do is we look at this one, and if it's soft, we'll remove that thing, okay? And then we're still left with all those particles here, right? And so we can then look at this one, right, and say maybe this is also still too soft, right? And we'll also remove this one, right? Of course, what we need is like a criterion that tells us what we exactly mean by soft, right, and when to stop, right? Because otherwise, I would just like go through. I need sort of an algorithm to do that, right? Otherwise, I just go through and throw out everything, and I'm not really left with anything, right? So I need to have an algorithm that tells me when to stop. And it turns out a very useful one is if we require that the energy of the softer branch here is larger than this quantity here on the right. So first, let's just set this theta here to 0. Then we just have a parameter here saying we choose that to be, but these are all quantities, z is something between 0 and 1. And here we basically require, for example, that this energy of the branch here is larger than, say, z cut, and z cut can be something like, say, 10%. Right? So if I find a branching here off that main, main branch that exceeds, say, 10%, then I'm going to stop. Okay, and so for example, this one was just 5%, this was 7%, right? And this one is 15%, right? I'm going to stop, and I will now my new jet are all the particles that are here, right? So these are removed. Everything here I will keep. Okay, and so it turns out that that's a useful thing to do. Right? It's not immediately obvious why that's a useful thing to do. But different than just like looking at all the particles and just removing the ones that are, say, 1 GeV, this is something that I can account for in the theory calculation. Okay, so the theory calculation is going to get more difficult than this, but it's something that I can account for systematically. Okay, I basically have to just change that, but then I can do it. And so There's still this additional dependence here, so I can modify this a little bit. So I should say, so z cut is something I can choose. I can choose that, for example, to be 0.1 or 0.2. That's just a free parameter. I can also make it dependent, not only on an overall energy cut, but I can also make it dependent on theta, where theta is the distance here to the main branch. And if I include this, then it will primarily remove radiation that's sort of at the boundary of the jet, right? That's where I expect, the main problems, right? And so I can also, in addition, include this. I can, set beta naught equals 0, but I choose a finite beta value here, and then I have also a dependence on theta, and that sort of predominantly removes particles or branches, I should say. Right? One shouldn't think of this sort of as particles, these are the branches. That not only contain, one particle, but they can contain, a set of particles, right? And then I'm going to systematically remove those, and I'm going to stop whenever, this criteria is satisfied, and everything else is what I would call my groomed jet. Yes.
In a typical jet, what percentage of the tracks get cut? What percentage of the energy get cut? My intuition is that 10% of the energy is still a lot of tracks carrying that percentage.
Yeah. So it depends, of course, what you choose for z cut and beta, right? That it will depend on that, and it will depend on the PT, right, of the jets. So you can actually that's actually been measured. So did you ask about the number of particles or about the energy that is?
I asked about the.
Oh, both. Oh,
see, because I expect that even if there's only a few that are getting 5%, even if it's 3 or 4, that's still 15-20% of your energy.
So typically these are really very, so I just made up numbers, say like that, 5 and 7, right? Like typically they're smaller. Okay. It's usually relatively, so this is like a quantity called like energy drop as a quantity you can compute, and that also has been measured at the LHC in particular. So if you go to, so at the EIC, that one has to be very careful, right? Because you have, say, 10 particles, right? If you remove some of those, right, you have almost nothing left, right? Then one has to be really, really careful. But at the LHC, right, if you already have 100 particles, maybe you remove 10 or whatever, right? They're usually very, very soft. But it's, so I can't, out top of my head, say what exactly the distribution is. It's like generally a small quantity. And it has been measured and also calculated. You can sort of define as an observable, right? And measure it and calculate as it turns out. Like the nice thing is that this particular criterion allows us to do calculations, and we can actually treat that as an observable. And it's usually it's small, but I can't unfortunately give an exact number. Yeah. But exactly. So if you go to lower energies, even if you go to RIC energies, you have to be careful to do that because you very quickly remove the entire jet. But it's possible, right? If I choose this as 0.1, right, and all the particles in the jet have 5% of the energy, right, then I will just remove the entire jet, right? So that's also a possibility. But the fraction of those events where that happens is very, very small. Right? Okay. And so let me quickly check. Yeah. So right. So I don't. We're not going to go into details of how you account for that in the theory calculation. Basically, what you have to do is to make that factorization more complicated, right? Because now you have parameters like beta, like z cut. They will also introduce additional large logs. So what you have to do is you have to refactorize that even further into more functions. Make sure you have all the logs that appear are summed. And there are also still open questions, right? Like this procedure here works really well for the jet masses I'll show in the next slide. But there's some observables where this actually doesn't work. And so like for some reason, this systematically and seemingly correctly removes soft radiation if I ask, for example, what's the mass of the jet? And I can sort of recover then by doing that, where I can recover this idea that one jet equals one parton, right? So if I do this, right, I basically recover this idea that I started here with a quark, right? And I remove a bunch of soft stuff that is actually, coming from outside the jet. And I sort of then recover the hard core of the jet, right? And that's really what I want, right? Of course, you're also going to remove a little bit of the radiation, right? That was actually coming here from the initial quark, right? We cannot distinguish on an event by event basis. Is that particular emission coming from outside the jet, or is it coming from the actual quark or gluon that we're interested in, right? So there's definitely some ambiguity there, but it's fine in the sense that we can account for it systematically, right, in the calculation. And then what we have to do is do a calculation and compare to experimental data, see if it actually works. That was for, for quite some time, that was sort of the question, does it actually work? And so you can see here some examples. We did a calculation of that, also other groups looked at that. So what is measured here by the Atlas collaboration is exactly this groomed jet mass. Right now, we're not looking at the sum over 4 vectors of the entire jet, but we just take the particles in this groomed jet that are left after this algorithm stops. We sum over all of those and then look at the mass distribution. Okay, and so what you can see is that cross section that is shown here, so it's a ratio to the theory, but if you look at this, the shape of the cross section actually looks quite different, right? So if before we had sort of like a nice peak distribution, right, for the jet mass, now we sort of have something that's kind of cut off, right? So it starts here out like the normal jet mass without grooming, and then as opposed to going up and having like a nice peak, it's kind of cut off here and like going down, right? And the reason is mostly because here you're not really removing much of the. If you have really a heavy mass jet, right, then the grooming doesn't really do anything. But then here, you would have a larger mass peak here, but you remove some of the soft radiation, the jet's going to have smaller mass, so in the thing they're going to end up somewhere here on the left, right? So we sort of get this kind of funny looking mass distribution. But the nice thing is that it agrees essentially with a few percent, right, with the actual theory calculation, right? So by using this kind of procedure, we can now, without having to model any of these complicated things, what I talked about, like the underlying event and all that, or even the hadronization, we can forget about all that, right? And we can just do a one-to-one comparison to perturbative QCD, right? So we can rely completely on first principles calculations, and we can directly compare to data, okay? And so in that sense, this procedure has been very successful to actually do one-to-one comparisons to data. And it sort of allowed us to recover this picture, right, that we want to have, that one jet equal one proton, right? That was sort of the main point why we're studying jets, right? And so we can make reliable perturbed QCD predictions. So this, I would say, sort of 3 points. One, we can now do direct comparisons. This has actually led to a lot of new developments, like theory developments and new observables. That I'll not really talk about, but there's something called Sudakov safe observables, right? So before, always talked about infrared collinear safe or unsafe observables. And that's actually not sort of the complete truth. There's sort of a category in between, which is called Sudakov safe observables that was developed basically because of these observables. They have very interesting properties. And we can now use this for BSM searches. So that was what I sort of was hinting at before. What we want to do, right, so we want to measure the mass of these groomed jets, okay? And that's what you can see here. So that's sort of in a different kinematic region. So what you can see here is the mass distribution. Sorry, this is, what's the scale? Okay, so these are jets between 7 and 100 GeV in terms of energy. And then you can look at this here as a function of the mass distribution. Okay. And so the mass distribution, okay, that's one additional thing applied to this, that's not too important. The mass distribution basically just falls off steeply, right? It's like a smooth background that you would get just from QCD jets alone. Okay. And now what we want to do is basically see if there are resonances, right? So if I, for example, could use jets that originate from Z or W's, right? Then I will have a lot of jets in a region around the mass of the W or the Z, right? And that's exactly what you see here, right? Here, this is not a smooth spectrum, right? And let me see. Yes, that's exactly where the W and Z is. Okay, so I cannot necessarily say on an event by event basis if this was a W or a Z jet, but I see that there's a peak in the distribution. Okay, because I'll produce more of the jets that are exactly in that mass region here. Okay, and so if I want to now search, for example, for Z prime or W prime, which are BSM physics or proposed models for physics beyond the standard model, then I should also see that here, right? So they did something here with like Z prime, and so we can basically see is there like an additional peak somewhere on sort of this smooth background, right? And that's really something you can't really do if you don't groom the jets first, okay? if you just measure the previous mass, right, where you just, collect all this like soft energy that's, floating in the event, then you cannot really do these measurements. But if you first remove the soft radiation systematically, then you can really use that as a tool to see if this is actually coming from a Z or a W. Okay? So it allowed us to do interesting QCD studies, and we can actually really use this now as a tool to do searches of physics beyond the standard model. And this is providing the most important constraints, for example, for Z prime and W prime, even though I don't know exactly, why that's, a particularly good a model or candidate for BSM physics, but it allows us to do exactly those precision studies that we wanted. Okay, are there any questions? No, all right. Then let's move on to the last part, which goes again, basically in this direction. So I think in the first lecture, right, I think I showed this, this illustration where we said, well, the Higgs particle decays to a lot of different particles, but most of them basically end up as jets, right? And only 2% are something else. And so, of course, what we have to do now, if we want to make use of these 98% of the cross section, is we have to be able to tell where the jets are coming from, right? So I already talked a bit about whether they're coming from like Z bosons and things like that. But what we want to know, right, like these 98%, like what's decomposition in terms of light jets, right? If they originate from up and strange quarks, if they originate from B jets, gluon jets, and so on, right? That's basically what we need to do, right? Like if we can do that, then we can make use of this 98% of the cross section, right? And of course, if you're like interested in like EIC physics or say nuclear modification, right? You're also interested basically are the jets that probe your nuclear matter of some kind, right? What's sort of the original particle that initiated the jet? And so the question is, well, can we tell them apart and can we make use of the 98% of the cross section? And potentially, can we do that with machine learning? So of course, what we have to make use of, right, as I already mentioned before, we have to like look into the structure of the jets, right, to tell whether this, what initiates it, what particle initiated the jet. And so, like a simple example would be to, or sort of a canonical example that people often use sort of to do benchmark studies, is to think about what are the differences between quark and gluon jets. That's partly a benchmark, but also very often, like BSM physics is expected to predominantly have a quark-like jet, or coupled to like quark-like or initiate quark-like jets. So being able to remove the gluon jets and keep the quark jets will enhance your signal to BSM physics. Okay, and so before we go into sort of like the details of how that's actually done and how well it performs, about a little bit what exactly we mean by quark and gluon jet. That's always something one has to be sort of aware of, that there's sort of some theoretical subtleties, right, of what exactly do we mean by quark and gluon jet. Do you guys have any suggestions of what we want to call a jet originating from a quark or a gluon? How should we define that in sort of ideally theoretically rigorous way, and in a way that we can apply to data, or one of them? Any thoughts? Anything thoughts?
You might want to look at the leading order tree level contributions to final state radiation.
Yes, exactly. That's one. That's sort of the first approach, right, that we can use. We can look at the leading order scattering, right? In this case, it's say gluon scatterings, where I will produce hopefully 2 gluon jets, right? And what I sort of do implicitly here, right, is I want to make a definition that's valid in the UV, right, the very high end. It's not in the infrared, right? And that's sort of the idea that we'll also use now to sort of then simulate. So we'll do that with a partial shower, right? We can generate events and jets, and we initiate them with a hard process. In that case, we would produce 2 gluon jets. So why would that? Do you guys have any suggestions? What's sort of the problem with that from a theory side if we do that? Any thoughts?
It's really hard.
It's really hard in what sense?
I don't know.
So it's something we can do, right? We can run Pythia, right, and we can fix the hard scattering process, and then say in this case we get, we cluster the jet with given radius and algorithm, and we'll get two jets, right? And we say that's a gluon jet, right? That is something we can do operationally, right? But it sort of has some issues why we might have a problem with that from a theory standpoint.
Is it about like maintaining the color neutrality?
Color neutrality? Not sure what do you mean by that exactly?
Like say, while quark and interacts with gluons, like the final outcome like has to be color neutral. Is that has anything to do with this?
I think it goes in the direction, right? They are basically, or at least if I understand correctly, what you're saying is there's going to be like a partial shower that we attach to this, right? Well, first it's just leading order, right? That's already a problem, right? We would want to go, to higher order, NLO, next leading order, something like that, right? So it's something that's inherently tied to leading order plus partial shower, okay? But then you run the partial shower and something will happen, right? And so to illustrate what can happen, right? If I sort of start, with a quark, right? Then I, for example, emit a gluon, and depending on the jet algorithm, right, I might identify this as a separate jet, right? It originated from a quark, but now there's just a single gluon in the jet, right? So what should I call that, right? And of course, it depends on the algorithm, right? So it's definitely not unique, right? And we discussed this the whole time, right? So if I start in this particular case, right, with a quark, then I actually get two jets, a gluon jets, and this one, maybe I should call that a quark jet, right? Because it has a quark line emitted a gluon, but the jet algorithm would put that together with a quark, right? So that, that one I can call a quark jet, but I actually produce two gluon jets starting from an initial quark. So that sort of makes this generally a little problematic. The next possibility we have, and that's sort of the best we can do at the moment from a theory side, is to basically use whatever this formula here gives us, okay? So basically what we said here, right, is we have this factorization. This jet function here originates from a quark or a gluon and carries momentum fraction z. And then we measure additional substructure variables to identify was it actually a quark or a gluon. That works also again. So this was basically leading order plus partial shower. This works at least to NLO plus higher accuracy, but currently we cannot really compute much beyond that. So it's not clear if that will work. And it only works at leading order, or sorry, not at leading order, at leading power in R. So for example, if you have the scattering here, right, say if these were all quark lines, like what could happen is that from the initial state, right, this initial state radiation that I mentioned, it can emit a gluon here, right, and can end up in the jet over here, right? And so then again, I have a problem, right? They're coming sort of from different origins, and then theoretically, I cannot even say anymore, is it a quark or a gluon jet? But I can do it at that order, and I can do it up to leading power. And for many things, that's perfectly sufficient, right? So if you do the grooming that we did before and so on, then that's all fine. So that's sort of the better thing to do, but it's not a partial shower anymore, right? So we don't have event by event information. And the last thing we can do, but we'll not use that. We'll maybe stick to this. But the last thing we could do is we can just really tie to the overall event topology. Right? This is really like now a measurable quantity. It's not dependent on any kind of theory considerations. What I could say is I'll just compare photon jet events, right, where I have, say, a photon or a Z recoiling against the jet, and I compare that to the case where I have dijets, so where I have basically two jets in the event, right, as opposed to that. And then in that case, like I know that the jet distributions are going to be different, right? Like this has a different hard scattering process than dijets, and so I may not be able to, directly say, event by event what I mean, but at least I can, require that particular event topology. But then, maybe it's not that useful anymore, right? Because, there's no gain basically, right? I already know sort of what event I have, right? I don't need to further discriminate this against dijets. So the main point is just there's some theoretical, ambiguities to all this. We can use machine learning, but there's always something one has to sort of keep in mind that there are limitations to it, partly due to theory considerations that we would like to understand better. And if we go to something that's really robust, right, where we sort of go to particular phase-based regions with overall topology, then it's not particularly useful anymore to actually define it. Okay, so that mostly the main point here is sort of to sort of have that as a caveat in mind, that there's theoretical things one has to be sort of careful about. Okay, but let's now not worry too much about it. Let's do the first one. We'll look at the hard scattering process, and then we'll basically just run a partition shower and see how well we can do this. And so to sort of get a baseline, right, how well machine learning can do and compare to, say, other more traditional techniques, let's first look at a set of observables that we can compute very well from first principles, where we know exactly what we mean. So that in that case, we actually stick to the second definition here. Here we can define what exactly we mean by quark and gluon jet, and let's see how well that does, right? And then we can compare it to how well a machine learning algorithm does. So I think Rabah already talked about neural networks last week, so I'm not going to talk much more about it. I'll just say sort of how we can use that here. Okay, so but to have a comparison, let's first look at traditional observables. And so let's look at what is called angularities. They're defined here. They're very similar to the jet mass. Actually, one of those cases of angularities or jet angularities is the jet mass. It's defined as an observable that assigns a particular value to all the jets. And so the idea is basically, well, I'll show the distribution on the next slide. The way it's defined is we sum up all the particles in the jet. We sum up their energy fractions, shown here, right? And we weight it by the angle of each particle to the jet axis. So sorry, this should be a theta ij. Theta ij is given just by the distance in the eta phi plane to the jet axis. And then that's raised to some power with some parameter a. Basically what that just does is it makes sure that if I have a very collinear particle, right, then it will have a very small angle, and then it doesn't really contribute to that sum, right? So if I have this theta dependence in here, that basically just makes sure it's infrared collinear safe, right? So it's something I can actually compute, okay? And so as it turns out, like the smaller tau a is, the more collimated is the jet, right? So if all these angles here are close to zero, right, then the entire thing is zero, right? And that's more or less what I expect for a quark jet, right? A quark jet, because the color factor doesn't emit as much, right? It's just a color factor CF, and so the jets are generally more collimated at the core of the jet, right? Then I expect the sum to give me, on average, a relatively small value, right? Whereas if I look at gluon jets, then that's going to be generally a larger value, okay? And so by then looking at this number, I should be able to, at least on average, figure out if it's a quark or a gluon jet, okay? And so let's look at these distributions. What happens if we do the calculation? This is the cross section here as a function of this parameter of this as a function of tau a. If you look at the sum of quarks and gluons, we get the blue distribution here. So it just peaks at some small values. And then we can decompose it in terms of quarks and gluons. I hope you can kind of see it that the red here is for quark jets. So it peaks at smaller values and then it falls off. Versus the gluon here is shown in green and kind of bright green. So I don't know if you can see this very well, but it's one, a broader distribution. Okay. And that's exactly what we expect, right? For quarks that are more collimated, we get a smaller value of tau a. If you look at larger values for gluons, get a larger value of tau a. And so indeed the distribution is generally broader. Okay. So that's, at that point, it's certainly well defined, right? And then we can try to use that, right? You can sort of put a cut here, right? Say, all the jets, so we, for example, choose a value of tau a, right? And then all the jets to the left, so maybe we want to put the cut here. And then everything that has smaller values of tau a are very likely to be quark jets. Anything above is very likely to be a quark gluon jet, or at least it's some kind of mixture, right? But for example, if I put my cut here, right, then anything with values of tau a smaller than that is very likely to be a quark jet. Okay. And so the way to quantify how well this works is quantified in terms of these what is called receiver operator characteristic curves, where I exactly look at how does it change, how good is my tagger if I basically remove this threshold here left and right. I'm not sure if Rabak also covered something like a ROC curve. Did he discuss that in terms of classification? No? Okay. So this is basically like what you saw before. Okay. So if I basically put a cut here, right, everything to the left, I count as quark, everything to the right, I'm going to count as a gluon jet. Okay. Then I'm going to make some error, right? And so this basically quantifies how well am I doing, right? So if I put this all the way to the left, right, then I'm certainly always right about the quark jets, but I basically don't have any. And if I put it all the way to the right and I count everything as quark jets, then I'm also doing very poorly, right? And so basically what you want to have is something in the middle, right? For example, in the previous case, right, you maybe want to put it somewhere here, right? Anything on the left you count as a quark jet, anything above, you count as a gluon jet. And then you basically count how often are you wrong, right? So for example, if I put my cut here, then everything in red is going to be right, but I'm going to make some mistake, okay? And that's captured here in this thing here on the right. So it's basically counting. So if I have a perfect classifier, it would be up here, right? I identify quarks and gluons correctly. And if I make a mistake, so if it would be completely random, then I would be sort of here in the middle, right? And I always make I'm just guessing randomly if it's quark or gluon jet, right? So again, it's 50-50%. And so what I want with this curve, so basically every point in this transition of this decision threshold, as I sort of move it from the left to the right, that's going to give me 1 point here on that curve, okay? And so the better the curve is, like the closer I am to this endpoint here, the better I'm going to do, okay? And another way to quantify it is if I look at this area here under the curve, that's going to quantify how well this classifier or this jet tagger is doing. Ideally, right, this area under the curve should be 1, right? This just square with area 1. So if I get something, a classifier that's closer to 1, the better it is. And a completely random classifier would be at 1/2, right? If I'm just guessing randomly, then I would be at 1/2. So I'll get sort of a value for the area of this curve between 1/2 and 1. Okay, and the closer I am to 1, the better. Does that kind of make sense? Yeah. All right. So let's take a look at what happens. So this is the distribution for the angularities that I've showed before. And now we'll basically move this decision threshold to the left or right. Right? So we'll basically check, how many do we classify correctly and how many we don't. And so what you see here is exactly this raw curve. For different values of this angularity parameter A. And you should probably just neglect here the blue curve. I think that we sort of pushed it a little bit too much in the non-perturbative region. But what you can see is that it sort of, it does okay, right? Like the completely random classifier would be here, just the diagonal, right? And it sort of does better, right, than the diagonal. And this one, is not going off quite right. What you also can see is that there's almost no dependence on A, right? So if I, modify A or change a little bit, almost nothing changes, right? And that is basically like a limitation of these analytic techniques when we do theoretical computations. That is referred to generally as Casimir scaling. So more general concept that people thought about, and it basically just means all we can do here is based on to first approximation, the classification here always depends on color factors, right? And we're basically just making use of that, like whether it's a CA or a CF color factor, and all sort of the standard observables that we can easily compute, they will always give us a raw curve like this, right? It just doesn't get much better. Okay, and that's sort of that's sort of like the traditional observables, right? Like when people thought about it from a perturbative QCD perspective, trying to make sure everything's kind of well defined, then that's sort of as good as it gets. So it can do a little bit better by sort of using these what are called Sudakov safe observables, but it still doesn't get much better than say the blue curve. Okay, and so that's then basically where you can try to use machine learning. No, I'm missing a slide here. That's very unfortunate. Okay. Yeah, so I had a slide where these two images were separate. So one way to do machine learning is to just use jet images. Okay, so well, basically, this is now an averaged image. So unfortunately, that it's not there now. How they're separated. But so basically, what we'll just use is we'll take this as an image. We look at it in this case from the top, and then we basically just plot as the intensity is the momentum of the particles in a particular pixel. Okay, so what is shown here is a jet image in terms of the pseudo rapidity or the rapidity and the azimuthal angle plane. And the circular ones are again, what you get for say anti-KT jets, and you average then over many of them. And then you get this, these type of images, okay? And as we know, right, as we saw on one of the previous slides, right, what is kind of hiding, unfortunately, behind this one is for a QCD jet, I'll basically just have one hotspot sort of at the center, right? And what this image is a W jet, right, where we basically have sort of these two prongs, right, because it's sort of a decay that gives us two hotspots, right? And since I average over this, it basically shows up in sort of these circular rings here, right? We have something important at the center, and then I have another sort of hotspot that is now, because I don't want to sort of orient them, right? They're sort of smeared out over many images, right? And I sort of have a second hotspot or a second ring here compared to these QCD jets, okay? And so what you then can do is you can use a convolutional neural network, right, that you say typically use to distinguish cats and dogs, right? And you run your filters over that in certain ways, right? And then you can ask, the convolutional network, is it a QCD jet or is it a W jet? Or is it, you can compare, for example, a quark and a gluon jet. And so in this case, the formula is a binary classification problem. In general, of course, you could sort of make it more general by ask, is it a quark jet, a gluon jet? Is it a W, and everything sort of together, right? And these were sort of the initial attempts to do this, and to basically just to directly use things from computer vision and directly apply it, to jet images. Since then, and I'll later show the rock curve or the performance on the next slide. But since then, there's been, of course, a lot of developments, right? People have tried a lot of different things to sort of improve that, to improve the performance of machine learned classifiers, and try to make a little bit use of the physics that we know about it. One example that's particularly successful, as it turns out, are so-called particle flow networks, or so-called deep sets, where you basically just don't really think about it, the jet having sort of a tree structure, right, like the Cambridge Aachen or something, but you just take it as an unordered, list of particles or a set of particles, right? And so it just basically says there's no, inherent structure to that. It's really just a set, group of particles. And so what you can do then is to just, you have to make sure, right, if there's no order to it, you have to make sure that there's permutation and variance built into your classifier, built into your neural network. And one way to do this is exactly with these, particle flow networks, is to have two neural networks. The first one basically takes as input every single momentum here that we have in the jet, right? So it's just a set of 4 vectors. Then we apply a neural network to that, right? Whatever network you sort of want to use, that's up to you to decide that. That acts specifically on this. And then we have a summation operation here, sort of in the latent space, right? This phi basically maps from the 4 vectors to some latent space. And then you have a summation operation, and that basically makes it permutation invariant, right? So if I shuffle here, if I shuffle my momenta here and I put it in here after the summation operation, it's going to be the same answer. And then I have a second neural network that we call here F, and that's that's basically the final output that just gives me then the binary classification score. Right, thanks. I'm almost done. And so in this case, basically a combination of 2 neural networks, one that's sort of acting on the 4 vectors, and then a final one to sort of aggregate everything. And so we'll just use whatever neural network you want, which is just a sufficiently flexible function that we can optimize the parameters, we can optimize its parameters very efficiently. And so let's take a look at how well that performs. That's what is shown here. This is again one of these rock curves, right, where the closer the curves are to the upper right corner, the better the machine learning algorithms perform. For comparison, you can see again here what I showed you before in terms of the angularities. Now here this is shown for the jet mass. That's just a particular example of these jet angularities, so the generalization. And you can see here, this is the performance of them, or of the angularities, and the machine learning is up here, right? So it does way better. And well, that of course has sort of been now around for some time, right? And people, well, it's generally very interesting, right? It just does way better than anything that we sort of as a community came up with, starting from first principles in QCD, right? And to some extent, that I would say that's still really an open question, right? We don't really know what the machine is making use of to get from here to here. There's apparently more information in these jets than we're sort of traditionally making use of, right? If we just use something like a jet mass to search for physics beyond the standard model, then we got whatever I showed you before. But apparently, there's potential to do way better, right? And this is, of course, done. These particle flow networks are definitely not infrared Collier safe, right? It's making use of all the information, of all the particles in the jet. That's absolutely not infrared Collier safe. But even if you design an infrared Collier safe machine learning algorithm, it still does way better, right? So there's both infrared Collier safe, so calculable information that's in the jets that we're currently not making use of, and there's also information in these jets that goes beyond what we traditionally think about. That's certainly non-perturbative. And so this is sort of one of the main questions I wanted to leave you with. That sort of requires further exploration in the future. If there had been a sort of afternoon session, we could have looked at this a little bit together. Otherwise, you're very welcome to look at this webpage from Jesse Thaler and friends. You can find the code here on their webpage. You can find the data set. You can just, for example, for these particle flow networks, you have the code available here. You can just copy it to Google Colab, run a Jupyter notebook. Basically, you can easily reproduce this plot here, right? So you will with a few clicks, you'll do way better than the perturbed QCD community came up with over the last decades. So it's very nice to play with, and if you have ways to improve it, that's of course great. And so the last thing before ending, I just want to mention, of course, the question is, can we potentially understand what makes these machine learning classifiers so much better, right? And so people have thought about how we can sort of make machine learning more interpretable, right? How we can potentially map it to observables that we can also understand from first principles. One way to think about this is in terms of so-called complete bases of observables. For example, there's some work in this direction also in the context of nuclear physics. These things are very important, right? Of course, the question is also, is it really useful to use supervised machine learning on these data sets that are generated with parton showers, right? Maybe one should just sort of use it as a benchmark, right? And then try to identify something that's more meaningful, right? Because I mentioned there's like some issues, right? What do we actually call a quark in a gluon jet? And let me very quickly skip to the end to just have conclusions. Yeah, so to wrap up, right, we discussed jets as sort of this window to very short-lived quantum processes, right, that ideally are sort of one jet equals one parton, right, and there's some problems with it. Sometimes we have ways to recover that. It's interesting because of this analogy, one-to-one analogy to partons is also relevant because the close analogy to parton showers, right, of the structure of jets. They're a very good probe of QCD physics, of hadronization, that Anselm we'll talk about again today, of Higgs physics, right, at very high energies. There are a lot of applications, not only at the LHC, but also at the EIC. That's sort of all the slides that I just skipped toward the end, because otherwise I won't be able to talk about it. But jet physics is really very important now, also at the EIC. It's also relevant for nuclear matter, right? If we'll think about heavy ion collisions, if we think about electronucleus collisions, those jets are very important, which I also didn't cover. And of course, there are like these machine learning algorithms that have, of course, now led to a bunch of open questions also of, what are we missing about the jets, right? And sort of from our theoretical understanding that we'll have to think about more in the future. So with that, thank you very much. And let me know if there are any questions.
So Felix. For the image neural network, there is some algorithm to highlight which part of the image are used to make the classification. Did you know if it was already tested on the jet algorithm?
A little bit. I think there's more to do in this direction. So what people have identified, so people have tried to approximate these kind of classifiers with more traditional observables. And one of the things they found, for example, is that what seems to be very important is if you have sort of like W, for example, that has sort of these two hotspots, then what is super important as sort of the third important emission. So you have definitely two, and the what was it? Well, the distance, I think, of the third to this dipole. I don't quite remember. There's a paper by Angela Koski. So sometimes it has been used to some extent, right, to try to understand what makes this huge difference. And people have identified some observables that can sort of help you to get better in this direction. But it's still not there, right? There's still a significant performance gap in machine learned things and things that we understand from first principles. So people have used some of those things. I'm not sure if they sort of haven't explored everything, right? And there's certainly the question of how to sort of map it to things that we can better understand from first principles. So some of it has been done, but there's still, there's still questions of why it does so well.
More questions? Questions from the audience?
Any questions from Zoom? Oh, I'm sorry.
What new challenges do you anticipate, dread, when doing jet physics at the DIC versus previous colliders that people are more familiar with?
Right. So I think first the goal is just going to be different, right? We'll not be searching for boosted W's, right? So the goal is going to be very different, and it's going to be. I mean, there will be some, I think, ESM searches that one can do with these type of observables, but the main challenge is, of course, that you're like at lower energies, right? And the number of particles is going to be very low, and so if you try to do perturbative calculations at too low energies, right, then they sort of break down. And it's very difficult to really quantify sort of where they break down, right? And where it's really useful to talk about jets, right? Because like sometimes people say, well, if there's, or I think one of the previous experiments said if there's less than 4 particles, then it's not a jet anymore, right? But that's not a really well-defined thing, right? Like, you basically have to do a perturbative calculation. You have to do it to sufficiently high accuracy. You have to understand non-perturbative physics very well to really say something meaningful about these jets at low energies. Being able to, for example, increase the precision is going to be important at low energies, and then try to get a handle on non-perturbative physics. I don't think I really talked about non-perturbative physics, for example, or at least not much. For example, the jet mass distribution that I talked about, right? There's like this shift going from the purely perturbative result to the one that includes non-perturbative effects and like all these other things that are shown on the left. Right? And so at the EIC, you can actually study this in a very clean way. Like you don't have, for example, you don't really worry about the underlying event, for example, if you have a DIS event, and you don't really worry too much about other jets in the event either, right? And so the dominant contribution in that case is actually the hadronization, right? When you go from particle level to hadron level. But then ideally you should understand sort of that transition a bit better, from first principles. And so what is done here, for example, is to use like a shape function that has a certain justification of why that is done. That's basically a smearing function. So you integrate that purely perturbative result against like a parameterized shape function. And that is sort of, right, here it's done in a way, it's sort of capturing everything, right? But at EIC, it would only capture hadronization. In that case, you can actually make first principles predictions of how, for example, that should scale, right? And that's sort of still not, I would say, sufficiently well understood to really reliably do that at the EIC. But it's sort of one of the things that I think one can do very well at the EIC, because here you have all this complication, right? And so at the EIC, it's in a sense simpler, right? But it's low energy. So I think the non-perturbative aspects of jets are, I think, are going to be very important and will be interesting to study. And I think that's where like a lot of more theory development also will be needed. Yeah. Thanks.
If there is no more questions, we can go to our break. Let's say Felix again.